Good evening, everyone. This is Mohit from the Electrical Department of IIT Madras. And first of all, I thank you all for inviting me tonight at TIFR and taking out your time to hear whatever I have to say this evening. Now, today I am going to talk about a topic called Unravelling Dataset Biases, which is rather unusual and perhaps is not theoretically intriguing, perhaps is not mathematically fascinating, and certainly is a topic which I have not been exposed to in the past, nor sincerely following in the present, nor do I plan to do in the future. And I must also acknowledge that I am a person who is not working on object detection, image segmentation, classification, a conception which you might have built while reading the abstract. But besides this disclaimer, I can really assure you that whatever information I'm going to say tonight is coming from the top brass papers published in CVPR, which is perhaps undeniably the most reputed conference in the computer vision community, considered better even than the journals. And why do I take this unusual topic? Is because I feel that this topic is of utmost relevance to anyone who is in the research community, and I hope that I will be able to convince you of this by the end of this talk. So to begin with, let's say that I am a bureaucrat and I have come to you knowing you as an engineer, and I want you to make a method or a model which can be deployed in a real world setting as shown on the screen, and it should work for images captured in the wild, for different occlusions, viewing angle, brightness levels, noises, something as you see on the screen, which is an example of object detection. Like when we record a real world scene using our camcorder, the camcorder is simply storing bunches of RGB pixels ranging in the value 0 to 255, but it really cannot parse through the scene. Instead, we humans, when we look at a scene, we look at high level details that okay, this is a human being, this is a fire hydrant, this is a tree, this is a sky, this is a road, and with this information we are able to do various subsequent tasks much more efficiently. And similarly, if even the camcorder can be made, if the machines are also made aware of this information, it could result in really nice applications. Another example shown on the screen is of semantic segmentation, in which we are not just interested in the bounding boxes, but we delineate a different color to each object. Say, as you can see that all the cars are in blue, and there's a specific color assigned to the road, specific color for the trees, and so on and so forth. And this really helps, such as say Google cars, for which operate in a driverless environment, to stay on the road and not bump the pedestrians on the footpath. Yet another example is of low light restoration. Here the images were captured late in the night, in near zero lux conditions, without any infrared technology, without any flash, just the normal way you capture using your favorite camera. and if we can still recover a good scene from the captured image. And you can think of all sorts of applications a bureaucrat can approach you for. Now I begin the discussion by starting with a typical machine learning research pipeline that we employ. Now we almost always begin with a data set which is supposed to be a proxy of the real world, and then we design or define a model. This model could be your time cherished support vector machines, it could be a naive Bayes classifier, it could be a decision tree, or if you are really fond of the recent AI boom, it could be the AlexNet, it could be the say VGG network, it could be the ResNets, or it could be say the generative adversarial networks, and there's a whole wardrobe of these models. And then we go on to after we have trained our model on the dataset, we go on to test it on the test data, and we define the accuracy. And even for this accuracy, really solid work has gone into that. What are the correct ways to what are the best way to benchmark algorithms such as ROC curves, such as precision recall, true positive, false negatives, F1 scores, and we really probably, I think you all are better off than me behind the math of all this. But and even if you look back at your machine learning career, I think most of your time would have been spent in understanding the models, developing more robust models, complex models, how to extract more efficient features, and really it is a predominant trend that it's really the model which is going to address the problems of the bureaucrat. But there is it's the data set which has almost always been ignored. I mean, you can ask for yourself, when was the last time that you heard a keynote conference talk or a good paper, say in CVP, RECCV, ICCV, or your favorite journal, criticizing criticizing how a data set has been constructed. By criticism, I just don't mean a rat race that the previous data set had only 10 categories and each category had just 50 images, but my data set has 1000 categories and each category has 10,000 images of various viewing angles, of various brightness occlusions, and hence it is bound to work in a real world setting. I'm not talking about these things. I'm talking about statistical analysis that has gone into to let us know that what pitfalls we have made in designing data sets so far, and what we can do in the future to really make good data sets. And the claim is that rather than now working very hard on the models and trying to get incremental gains on the performance by analyzing and making changes to the model, a much simpler model can give you much better results if it is exposed to a relevant and a properly constructed data set. And thus it is quite essential to understand how data sets are formed, what are the various biases that go into data set. I'm not going to cover them all, but some of them, so that you have a fairly good idea of different data set biases. Now the first bias that I am going to discuss is capture bias. To illustrate this, on the screen I now flash various objects, and these objects, I mean, I'm sure that all of us sitting, or all the audience who is hearing this talk will be able to correctly classify all these objects, such as, I mean, we see the chair, we see the oven, we see the microwave, we see the bottles, the pear, we see the computer, a banana, tap. I mean, it's a fairly easy task for human beings. But now I ask you a second question. I give you the image of a car, and you need to tell me that this image has come from which data set. Probably a very foolish question, probably a question which has nothing to do with what the bureaucrat has asked you. I just have to identify what the object is, and it is car. How does it make a difference that if I am able to tell you it comes from the Imagenet, or it comes from the Pascal dataset, or it comes from the Label Me dataset? But when researchers at MIT, they reported their findings in CVPR paper, they found that the first question is quite hard for the machines, and the second question turns out to be way more simpler for machines than expected. I mean, they simply trained a 5-way support vector machine, and the odds are that a random guess will get you 20% of the times that you are correct, but a simple SVM trained with minimal amount of data and minimal amount of time could easily fetch 70% accuracy. That is, 70% of the time it could tell you that this image is coming from which data set. And a repercussion of this is shown now on this screen, where a model is trained on a particular data set, say the Caltech data set. And a model trained on the Caltech 101 dataset, when tested on Caltech's test data, gives you almost 100% accuracy. But when it is tested on the Sun dataset, it drops to 20%. And this trend is not just for the Caltech dataset. We see a very pronounced diagonal that cross dataset generalization is really poor. Now this is not expected, because in the beginning only we said that the data set is a proxy of the real world, and if all the data sets are a proxy of a real world, or at least they tend to be, it doesn't matter on which data set you are testing and on which data set you trained, it should give good results for all the test data. But this does not, but this does not happen. And really, in the light of conventional machine learning, the very obvious answer would be, oh, it's the classical case of overfitting. The model has learned all the examples in the training set, and hence it is not translating to the test set. It's even valid today, but I want to emphasize that it's too early to blame the model. It's really the problem in the dataset. I again take you back to the images from the 5 dataset, and you look for yourself. If you look, say, at the Imagenet dataset, for it the car is really a racing car. Similarly, the CARTEC 101 dataset is really embracing car images which have been captured from the sideways. Similarly, for the label me dataset, a car always have some occlusions. So if in a dataset the car is defined to be some non-canonical viewpoint, say the rear of a sports car, then no matter what optimization algorithm you use, what benchmarking you use, how good your model is, the model is destined to perform very badly in a real world setting because it has no idea of how different because it was just exposed to the rear view of a car. So really, datasets need to be improved. Now I describe a second bias which happens in dataset, which is known as selection bias. To begin with, I show you the image of a butterfly, and what I do, I decouple the foreground from the background. The foreground is shown on the image on the top, and the background is shown in the image on the lower side. And now I ask again a very stupid question, a very non-relevant question: do backgrounds contain signal? I mean, if my task is to classify the butterfly, is the background important? Now again, some researchers at MIT, they actually took 9 categories from the Imagenet dataset and they did the decoupling task. Say on the screen you see the image of a dog, the dog is removed and only the background remains. And then the model is trained just on the backgrounds, and then at the test time it is again showed just the background images, say from the dog class and the fish class, and 50% of the cases it was correct, while it just had if it was just making a random guess, it could be correct only in 11% of the time because there are 9 categories. But even without the foreground, which is really the category, just by being trained on the background, it is able to give you good accuracy. And even when the information of the foreground was given, the accuracy in fact dipped from 50% to 49%. And this is not something new. Even the humans use contextual information to parse the scene. Say in the ImageNet, but the problem is really severe for the machine learning models, because if the foreground is removed from its usual background and placed on some other background, the model is really making a non-relevant classification. Say in the ImageNet dataset, if you look at the fish category, it is always captured fishes with after they were caught by a fisherman. So even if you blur the fish in the foreground, if you just see an image in which a man is holding some object, most likely if you say fish, you will be correct. So this is an example of selection bias. I now give you another example of selection bias, which is little bit more subtle. On the screen, I now show you 3 images, and these images were given to a classification network, and the labels obtained are shown as on the screen: monastery, some breed of dog, bull terrier, and stage. But when we proceeded for the benchmarking, the model was incorrect on all the cases, and the correct labels which were given by the annotators of the like the actual labels which are present in the dataset are shown in red. Now technically the label stage is very different from acoustic guitar. The label monastery is very different from the church. So technically, yes, the model is wrong, but ask yourself, is the model really wrong? Was the label stage incorrect? The answer is no. Even those labels were correct. To understand why this happens, let us now see how are datasets created. Before discussing how datasets are created, what is the utopian way of creating a dataset? We capture images in the real world, and once we have those images, we give it to expert annotators, and then the annotators they give a befitting category to each image. Say that it's an image of a dog or a fish or a cat. But the problem is this way of creating a dataset does not scale to millions of images as it is common for datasets today, which have up to millions and I think even billions of images. So how actually large datasets are created today is that the organizers, the creators of the dataset, they first fix the categories. Okay, I need to have category dog, I need to have category of primates, then in primates I need to have say gorilla or chimpanzees, or in the dog it could be the bull terrier. And once you are really have decided that these are the labels, now you crawl the web. You go to Google Images, you go to Flickr, and you search images which are returned for these categories. And once you get these images, now you send them to say Amazon Mechanical Turk. And the mechanical the users at the other end of the Mechanical Turk, they just have to say yes or no that whether this image is really a bull terrier or it's chimpanzee or a giraffe. To give an example, say you see the image as shown on the screen, and this image was obtained say from Flickr after I typed acoustic guitar. Now once I got this image, I put this image on Amazon Mechanical Turk, and I'm just asking the people, does this image have acoustic guitar, yes or no? And people will say yes, and then they come up with the creators have some relevant metric called the selection frequency, the number of yeses divided by the total number of instances. If the selection frequency is high, which probably for acoustic guitar in this case was very high, the label acoustic guitar was assigned to it. Like an example of selection frequency is also shown on the screen. You type throne on say Google Images, and these three images turned up, and for the rightmost image you get a perfect 100%, and this the label throne is assigned. And say for the left hand, the image on extreme left, the selection frequency is just 36%. That is, various people on Amazon Mechanical Turk, they said that no, this is not a throne. And only 36% people said that yes, so probably it didn't went through the dataset. Now the problem in this way, and in fact various datasets today such as the Imagenet are created this way. But the problem is that the images and the labels were treated in isolation, which is really creating the problem. The correct way of how a dataset should be created is something as follows. On Amazon Mechanical Turk, you show the people the image, and then you give them all the 1,000 classes in your dataset, and then you ask whether this image has grass, whether this has a bottle cap, does it have a eft? I don't know what a eft is. And then the anode and mechanical Turk people have to say yes, 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 or no, no, no. And I mean, they just have to, they have a checkbox. The problem is it does not scale well because human beings are really not trained for this task. I'm not criticizing Amazon Mechanical Turk. They really do a really good job and they really respect the rules and regulations which are laid down. But I mean, if given an image, I ask you which of the following 1,000 objects are present in the image is something really human beings are not designed for, and hence this approach does not scales well. And the previous approach that I just give you an image and I ask you whether acoustic guitar is present or not, it's just say yes or no. It works decently well, and that becomes the dominant practice. There are several ways to overcome this. Say you take an image and you take pre-trained models on say Imagenet. You take winners of different years, and then you take top 5 categories from each of them, and then you say have 4 models, and then you just ask, instead of 1,000, you just ask these 20 categories to the Amazon Mechanical Turk people that whether it has these, and this is not as difficult as identifying 1,000 objects, but it sort of helps you overcome the selection bias. So I mean there could be various other kinds of biases, but I think that you now have, by this time you have a fairly decent idea of what kind of problems can go in creating a data set. But now I discuss the repercussions. The data set is really meant to be a proxy of the real world. And there is no reason that why a data set, a model which performs bad on a data set should also perform bad in the real world, or vice versa. The typical way is that people come up with the training data, then there are some researchers who make the model, and then they test the model on a test data set. And once the model gains popularity, the whole community is now just after that single test data. And now what matters is just a single metric, say the precision metric on that single test data, which is going to decide which model is state of the art, the SOTA performance. The problem with the thing that is now worrying in the computer vision researchers is that probably by this approach we have narrowed down our original ambition of what the bureaucrat demanded, that I want a method which should work in the real world. But there is no reason that we have now started to chase after this single test data, and we are just obsessed with this single test data. And the problem is that a brave, new, innovative idea always have its initial hiccups, and probably in the beginning it won't be able to compete with the kingpins of the current technology. And because it is underperforming than the current state of the art, even the idea is refreshingly new and it has some promises. Because it is underperforming on a particular test data, it won't go through say a CVP or ICCV or ECCV, and it will fail to get the attention. People now give more time analyzing the ROC graphs, the precision recalls, than actually looking at the pixels and trying to understand what is fundamentally not fundamental problem with my model, or what further advancements can be made in the computer vision community, or for the matter any other field. And we are just stuck with this, and this is just because this aspect of dataset has not received sufficient spotlight. There are several other problems with this approach. One problem we already know, classical overfitting, and this problem is now accepted in the community and it still exists, but there's something called as adaptive overfitting. That is, once you train a model on a dataset and you get its accuracy on the test data, now you can analyze your accuracy, and you say that for this particular class, say for the fish class, I'm not getting good accuracy because perhaps the fishes are small, so I need a larger receptive field. So let me just increase the kernel size, let me increase the depth of the model. So in a way, and by repeating this process again and again, the test data is now no longer incognito. The model has really seen on the test data via indirect means by taking feedback from the accuracy. And this is in technical writing known as p-hacking the test data. So from overfitting the training data, we sometimes overfit the test data, and the consequences are, it doesn't stop there. It goes on to overfitting the whole benchmark itself. All I care is that how good my top 1 accuracy or my top 5 accuracy is on the Imagenet. That's it. And all it cares that who is the winner of this year. And in a again analysis done by researchers at MIT, it really did not matter among the top 10 models when they were analyzed statistically. They were roughly all the same. It's just that one model got the top place and it got the limelight. And perhaps this is the problem which has caused a lot of blasphemy. I am using a very harsh and a strong word to the research community, that you just are after publishing slapdash papers which have no relevance for the industry. I mean, an example is shown on the screen. I hope some of you are aware of word embedding algorithms. Google and Amazon, they are really working on it. So a model recently, it learned that what man is to computer programmer is something what woman is to a homemaker. Now this is not because something which is intentional. It is not something because you are not using state-of-the-art technology. It's something that perhaps the Wikipedia pages which were chosen for this particular data set caused the model to learn this. And this has really caused various a big racial fuss on the news, on the social media in the recent times. I mean, recently I was hearing a news that a machine was trained on human behaviors, and it was used by US courts to identify whether the witness is speaking the truth or he is a liar. And recently the company which created that machine was sued in a court that it favored the white people over the black, because given the same charges under same circumstances, if just because the person happened to have a blacker skin tone, he was labeled liar. And if a person just because has a fair skin, he is true. Now it is not something I say it was intentional, but just because, again, a data set would have been created as a proxy for the real world, and the model learned it that way. And I don't have more to say on this topic. Just I wanted to say that really the time has come that we work even on the data sets, and working on the data set can really fetches the next milestone in computer vision than probably working. I mean, obviously, I'm not saying that we should not work on models and algorithms. Even in fact, I am going to continue to work on models and algorithms, probably because I was never trained on how to think along these lines, and hence I thought that let me talk about this aspect, which I think could help many of us. Thank you.